Thank you for the invitation. I'm very happy to be in Oxford again, and thank you for staying until the very last session of the day as well. So today I will present this work with a very large team. It's been quite a journey, and it's not finished yet, hopefully. So I'm very excited to talk about less. This is the outline. The talk is not very long, but essentially I just want to justify why we did what we did, because it's a little bit different, and say something about code equivalence and make some considerations about less in the end. Okay, so this is like my usual slide about coding theory that I have in all my talks, and in this case it's really redundant, yes, but I still include it here for like 30 seconds just to point to the fact that usually when we consider coding theory, we worry about error correcting codes, and it's really crucial to have like an algorithm to correct error, because this is like our trapdoor, right? And so here I point out that we're working on query codes, and we define this code with matrices. There are many choices for these matrices. It will all come together later. So, the first thing you do when you think about coding theory is like, oh, it's hard actually to correct, right? Unless you have this error correcting algorithm. And so this is SDP in a very short, concise presentation. And, for encryption, this actually works very naturally since McAleese, right? This is like at the very beginning of public key cryptography. You just have a trapdoor that is very intuitive. You just have a code that you know how to decode and you mask it. Yes? So, for example, what McAleese or the writer do is they use a change of basis, right? So one of these many matrices, and then you go into an equivalent code via permutation. And by equivalent, I mean that it has the same weight distribution, right? So then this kind of completely masks the structure of the code. Well, in fact, this depends on what code family you're using, right? In fact, most often than not, it actually doesn't work, and the code's still too easy to recognize. And then you have structural attacks, but for example, for binary COPPA codes or LDPC codes or other stuff, then you're able to do this. And so this is actually very good for encryption. So now we have some candidates in the very last round of NIST for the first call that kind of all do the same thing, right? But for signatures, I'm old enough to say that, this has been around for a long time, this problem. So if you do kind of traditional ideas, they don't really work very well. So like the CFS scheme, very impractical. The Stern schemes give you really long signatures. So you have to do things a little bit differently. And in fact, we've seen, for example, yesterday, one answer is using MPC in the head schemes. Then you have this amazing soundness. And so you have to really modify the protocol a little bit. Or what we thought about doing is actually doing something entirely different. So rather than working on a protocol, working on the idea of the problem. And so, McAleese implicitly, right, actually, obviously, it requires to keep the private code secret, right? Because otherwise, there's no trapdoor. But what is the hardness of masking the code per se? Right, this is kind of an interesting question. And so in McAleese, you just publish the public key, which is the public code, and is obtained via SMP. But what if I publish the other code as well? And I'm not interested in the error correction capability per se. But so I can look at this pair SMP as anisometry, and isometry just means that it preserves the distance. In this case, what we're interested in is the weight distribution, so the entire collection of weights of the code words. And in fact, the problem of finding this map is well known in coding theory, right? So for coding theorists, it's interesting to have codes that have the same weight distribution, and that's why you look at equivalent codes, right? And when you look at it this way, in fact, it's just a type of isomorphism problem in the coding theory setting. So this is similar to isomorphism of polynomials, to the isogeny case, or to the lattice isomorphism problem that we saw earlier for Hawk. So they're all kind of like relatives in this idea. It's like I have two objects that are mapped via an isomorphism. So could we actually use code equivalence by itself? And the answer is yes. I mean, at least we did. In 2020, we constructed a very, very simple zero-knowledge protocol that is based only on the hardness of the code equivalence problem. And then, of course, once you have zero knowledge, you do your procedures and iterate, etc., and apply Fat-Shamir, and magically you have a signature scheme. So this is the basis of less. Okay, so what are these isometries? Well, one we've seen already is permutation. Of course, if you're looking at Hamming weight, permuting a vector keeps the same weight. Right? You're just moving positions around. The zeros remain zeros, and the non-zeros remain non-zeros. But you can do something a little bit more sophisticated, very little bit more sophisticated, which is scaling as well. So again, if you scale by some non-zero factors, then zeros remain zeros and non-zeros remain non-zeros. So this is a more sophisticated, more generic version, which we call monomial. And so like permutations, we can represent it as matrices and call monomial matrix product of permutation with this kind of diagonal matrix with non-zero coefficient. In fact, we can throw a field automorphism in the mix. But in cryptography, this kind of really doesn't add any complexity to the attack. So usually we kind of tend to ignore this. And in fact, we work on prime fields most of the time, and we just don't even worry about it. But still, this is kind of like the most generic notion you can have. And so one thing that is interesting is that it can be seen as a group action. And I don't recall seeing explicit focus on group actions earlier in the workshop, but essentially, we have many of these in cryptography, right? Ever since essentially Diffie-Hellman. But in our case, the group that is acting is the group of monomial matrices, and it's acting on codes, right? So it's not acting on a group, but it's actually acting on a set, which is kind of very roughly defined. Here we can think about just, for example, the set of generator matrices in row-reduced echelon form. So this is, each of these represents a code, right, in a systematic way. So we can think that, the monomial group is acting on the codes themselves, and we can represent it very easily as a product of generator matrix times Q, and then we just take it in systematic form. Or, we're using here row-reduced echelon form because in some cases it's possible that you don't have an invertible matrix on your left submatrix, and this is still fine, right? So this is kind of like an easy formulation of code equivalence as a group action. And then we say the two codes are equivalent if they are connected by an isometry, which makes sense. And we talk respectively about permutation linear or semi-linear case, depending on the flavor that we're interested in. And deciding, in fact, whether two codes are equivalent or not is the code equivalence problem, which is, again, well known in coding theory. And in fact, it's well known because, in principle, you don't know whether two codes, if you just take two random codes, you don't know whether they're equivalent or not. Actually, most likely not, right? So it's a decision problem. In our case, we want to use this for crypto. So we're interested in the vectorization problem for the group action, which is the search version, the computational version of code equivalence. Okay? And so we can formulate this, again, very intuitively, just given two codes, find the map that brings C0 into C1. This we can look at it with generator matrices, if of course we take G0 for the first code, G1 for second code, and then we look for monomial matrix Q that brings one into the other. And notice here that by using the ref, I am skipping quickly over the fact that we have a change of basis in there, but we just kind of choose the convenient one. Yes. Okay, so what is less at this point? Very simple. So I'm going to show you the zero knowledge protocol at the base. We don't need to go over the entire formulation of the scheme because it's very simple from that. So it's a key generation is intuitive, right? It's just a standard blueprint. We just take the two codes, right? So one is generated randomly, and then the other one is obtained via the secret map and constitutes our public key. So we set up exactly an instance of the code equivalence problem. And then it's a simple three-pass scheme, right? So again, traditional blueprint, we generate another instance of the same problem, right? Ephemeral instance via matrix, say, Q tilde. We commit to it via hash function, and then we respond 0, 1, and we show that we can kind of complete this diagram either from the public key or, from the public code G0, okay? So we can either verify from G0 or from G1, and this is it really, yeah? So this obviously gives us a scheme with standards 1/2. The properties are extremely intuitive, right? So completeness is obvious. Honest verified knowledge is also more or less as obvious. Right here, the only thing that is not random is this part, but obviously it's a product of two monomial matrices, so this is distributed pseudo-randomly. And so the two special soundness is also super intuitive, so we can show that we can extract a witness for code equivalence if you're able to solve, right, both challenges. So then, we want to turn this into a signature. We have to do parallel repetitions. Well, this is really the obvious way to do it, but of course you can do better, right? So rather than do T parallel repetitions, we can improve it. This is what we did in 2021. First thing is a kind of standard, again, with this kind of protocols, is you can use multiple public keys with non-binary challenges. And now instead of having G0 and G1, you have G0, and then G1, G2, G3, G4, etc. And then you can show that you're able to complete the diagram from any of these public keys. So then, of course, your soundness is going to improve. Yes, Thomas? It's the number of bits. Yeah. There's the bit, so you take the bits L at a time. Yeah. It's 2 to the L. It's 2 to the L. Yeah. 2 to the L. Yeah, of course. So like you can see there, like the public key increases very quickly because it's exponential, right, in the number of bits. So if you have like 4 public key, then you have like 2 bits, right, and then so on. So you can reduce the soundness, but yes, the key grows very quickly, and this is the first trade-off. And then the second thing you can do is a little bit more technical, but essentially, every time you have a purely random object, as most of you know, you can just send a seed for a pseudo-random number generator, and so this is much, much shorter, unless you're doing cross, than your actual objects. And so it's convenient to send a seed rather than a monomial matrix, right? And so you can actually try to send as many seeds as possible, so you make the string longer, you change the distribution, and in the end you have the same kind of probability, right? But then, so you have a larger number of iterations. So you have like a shorter signature, but the number of iterations is larger, and this can kind of make the scheme more costly. So overall, it's like 2 trade-offs that we can incorporate into the basic design. And again, these are kind of standard for zero-knowledge schemes. And the nice thing is that, these do not affect security. So all we need to do is like tweak the forking lemma or base our security on some completely equivalent problems like multiple code equivalence and stuff like that. So there's no security loss in that. Yeah. Okay, so like I said, we're not gonna look at the specific protocol because it's literally just this, yeah? It's just an iteration with some flavors. I think it's more interesting to actually look at code equivalence per se, because it's a new problem used by itself. And again, the thing that demonstrates this is that, we considered it for a long time in coding theory, but as soon as people started looking at it in crypto, then much more things came out. And so first of all, we know that PEP is not NP-complete, unless the polynomial hierarchy collapses. And also we have like a natural connection with the other isomorphism problem, right? So for example, we have a connection with graph isomorphism, and we know the graph isomorphism is solvable in quasi-polynomial time. So this is kind of like not encouraging, but also not necessarily dooming, And in fact, the same authors conclude that PEP is like not necessarily easy. So we're talking here just about the permutation version, which is the simplest case. But of course, there is a reduction, right, in polynomial time from one to the other, which means that if you have a solver for the permutation case, you can also adapt it to the linear case. So we can look at permutation case as a blueprint of what can happen. And what can happen is that we actually have very efficient solvers in some cases. And this depends on what case you find yourself in, right? So for example, the support splitting algorithm, which was around since 2000, is looking for invariants. And this, again, was coming just from coding theory, right? So it's actually looking for distinguishing codes that are equivalent from codes that are not equivalent. So it's the decisional version. And, of course, if you have 2 codes, what can you do? Compute the weighted numerator function, and then you just see if the 2 codes are equivalent or not. But this weighted numerator function is huge. So you cannot do it on the full code, but you can do it on something smaller, like the hull of the code, which is the intersection which is dual. And the hull of the code actually preserves the map, in the sense that if 2 codes are equivalent via certain permutation, then the 2 hulls are also equivalent via the same permutation. So you just look for the hull of the code, and essentially the algorithm runs in times that is exponential in the dimension of the hull. And now, of course, random codes most of the times have really small hulls, which makes the attack practical, right? So you actually can solve this very quickly if the code has a random hull, has a small hull. And so what you can do, what is in the algorithm, let's say worst case, right, is like, okay, I cannot distinguish them if I take weakly self-dual codes or self-dual codes, because these have maximum dimension. But for us, this is the interesting case. So you can just take self-orthogonal codes, this is what they're called, and then this avoids the attack, right? Because then the dimension grows very quickly. Now, for the linear case, what you need to do is to apply this, but not to the code, but to its closure, which is an expansion of the code. And then Sandrine also shows that these codes are always self-dual as soon as q is greater or equal to 5. So for the linear version of the code equivalence, we can just use random codes, and we're fine. And then we have various algebraic solvers that we've seen, again, as a theme recurring in most submissions, I guess. For example, Saeed Taha showed that you can set up a system of equations. You can always do that, and then apply group Bernoulli basis to solve it, right? There is also a way to exploit the reduction to graph isomorphism. But both of these techniques are essentially only efficient, or they just simply work only if the codes have trivial hull. And trivial means empty intersection, right? So it's kind of the opposite case. So in the end, we can easily identify these weak instances and avoid them. I hope I convinced you about this. And so what can we do if we cannot have an easy way? So like, what if we are in this like super worst case and we cannot apply any of these efficient solvers? So the coding theorists would be desperate. but the cryptographers are happy. And so the last thing that we can do is just try to guess the map from the code words with the same weight. Right? So obviously I take the two codes and I list all the code words of a certain fixed target weight, and then I just, of course, these have to map to each other somehow. So then I can deduce the permutation from this list of code words. And so this is the idea of Leon, and again, it goes really, really back, right, 1982. And in fact, if you get a moderate weight, so of course you can take the minimum weight of the code, right? But you have to also consider that you could get spurious solutions if you get too few code words. So you increase the weight a little bit more. As in practice, you can take, say, minimum distance plus 1 or 2. Yes, and then this kind of improves the performance a little bit. And the attack then is simply find enough code words and then match to extract the permutation. And this is but obviously the finding code words part is the lion's share. Yes. So the cost is essentially cost of ISD plus some linear algebra. And an ambulance, who is sitting somewhere in the room maybe, or was, showed us that in fact you can do better, right? So you don't need to find all the words. As soon as you find enough, then you can exploit the fact that permutation preserves the multiset of the entries as well. And so the attack goes better. And this is a probabilistic algorithm that is advantageous when Q is large, right? So if you have larger Q, then the multiset is more uniquely defined, and then you can use this to your advantage. And this attack actually outperforms the Leon technique. Okay, so in the end, what I want to focus on is the fact that if you avoid the weak instances, then the best attacks consist of using ISD to find code words, which is nice because ISD is an animal that we know and we can control very well. It's like basically, right, the basic threat for all the rest of code-based cryptography. So this is nice. And so for less, we parameterize very conservatively by just making the cost of ISD hard enough, right? And then the particular nature of less with the zero knowledge structure allows for quite a lot of flexibility because we see that we have these variants and we can choose how many public keys we want to use, what kind of fixed weight in the challenge string, and we can modulate many variants. Of course, in this case, we kind of restrict it to 2. At level 1, we have a little bit more granularity, but essentially we have, for example, a balanced set which yields similar sizes for public key and signature and minimizes their sum, or we can try to push for really small signature and lose in public key size if this is a goal that needs to be achieved. So this is technical details about our symmetric crypto, essentially, but usual stuff. And I think at this point we can consider seed trees usual stuff as well. Whenever you have to send a bunch of seeds, you'll just send them in a tree. Okay. So of course the choice of protocol parameters has a consequence on the performance profile, where T is the number of iterations that you do, and W is the number of them that correspond to actual monomial matrices versus the seed, and S is the number of public keys. So you can see that the public key, in fact, corresponds to S-1 generator matrices plus a seed for G0, and the signature, the salt and the digest, etc. But essentially, we have W monomial matrices, and then the remaining T minus W correspond to the seeds that are sent via the seed tree. Yes, very simple formulation. So these are the parameters that we get for the 3 security categories. Like you can see, we have the first set where we have more or less balanced results with this signature size 8.4, which is in the by now usual range for zero knowledge schemes, and a relatively large public key of about the same size. And then we can increase the public key, right? We can double it or triple it, and then the signature gets smaller and smaller. And then what's the cost, right? What's the benefit? And then we have the similar simulation for level 3 and 5. And regarding performance, of course, the elephant in the room is that each iteration requires a row-reduced echelon form, which is a Gaussian elimination. Yes, and so this really dominates the cost of computation, and it just scales according to how many row reductions you have to do. So the interesting thing is that less keeps getting smaller. So this work started in 2020 and it's been improved several times. So this is my funny slide, but also is my good slide in the sense that, since the original less work, we have the first improvement via these 2 simple variants with the fixed weight and the multiple keys. And then we have a recent improvement that is going to appear at AsiaCrypt 2023 with Paolo here. And we were able to about half the size of the signatures just by committing to an information set rather than the full amount of columns. So we show that this is enough to represent the map. And in fact, then once you open the door, you just go down the corridor, and we have an upcoming work also with Paolo and with Tony. And they're nice, they're sitting in the front row there. And so we show that we actually can define canonical forms for these maps, and they can be represented very compactly. So the current spec includes the information set modification, and we hope to be able to include the canonical form improvement in the next round of the submission. So the effect, just to give a spoiler, trailer, is this. So the current parameter would about reduce by one to 1/3 of the size. Okay, so now this starts to be really interesting because these are among the smallest sizes that we've seen so far. Certainly smaller than all the other zero knowledge schemes that we've seen, unless you're doing ski sign or something crazy. Okay, and I count ski sign among the crazy things. Okay, so this is a work in progress, which is very nice on reducing signature size. And what else are we doing? It's a good question. We are working on an AVX2 optimized implementation, which is not finished, which is why I didn't show you any timings, because showing timings for the reference code, unless you do cross, is not very significant for us. And then we do have a hardware implementation by Chris Guy and his group that was presented at PQ Crypto recently, and they showed that they're able to obtain a 2x speed up. And then one thing that is worth noting, which is about the last thing that I want to say, is that the particular group action structure that is at the basis of less actually has a lot of implication in other areas. So we were already able to develop ring signature schemes. Thank again to Bulens for the inspiration. And we are designing threshold signatures, which is a preprint under submission. And then we are also designing blind signatures and so on. And so this is really something that is missing in the panorama of post-quantum cryptography. And we're very happy that we're able to do this thanks to the group action structure.